and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we're going to be doing Unit 4, Lesson 1 on proportional variables. Obviously this is the first lesson in Unit 4. And Unit 4 is all about what we call dilations and similarity, but we start with a topic that you saw in both Math 6 and Math 7. And that's the idea of two variables being proportionally related to each other. So let's start by reviewing some basic things. Now, one thing that you're definitely going to want for this particular lesson is you're going to want your calculator. I'll bring mine up in a little bit, all right? But make sure that you've got your scientific calculator handy. Some of the work we're going to do today is going to be a little bit ugly in terms of decimals and things like that. Anyway, let's review some basics from Math 7, all right? If I've got two variables, call them x and y, and remember variables just stand for, quantities that could be changing or that we don't know or whatever. But if they're proportional, then what we know is that when we take one variable and we divide it by the other, then we get a constant. We would say that their ratio, the ratio of the two variables, is a constant. Now, another nice way of looking at this is literally by rearranging this y divided by x equals k into y equals k times x, because then it gets to a very basic idea. One variable is just a constant multiple of the other one, with that multiplier being k. That multiplier is called the constant of proportionality. Sometimes it's called the unit rate. There's a lot of different names that we give to it. Oftentimes they depend on the context, like what the problem is all about. But the plain fact is it's just telling you how big y is compared to x. So like if k was 2, then y would be double x. If k was 5, then y would be 5 times x. If k was 1/2, then y would be half of x. If k was 1/4, then y would be 1/4 of x. Always, all right? But the real key is when two variables are proportional, then when we divide one by the other, we always get the same number, all right? So let's take that and see what we can do with it. Here we go, exercise number 1. In science class, Maria measures the distance two objects have traveled at certain times. The results are shown in the table below. Letter A says, one of the two objects has a distance that is proportional to the time it has been traveling. Determine which one and explain. All right, so in other words, let's just make sure we understand the physical kind of thing that's going on, then we'll kind of get into letter A. Here we've got Maria. She's in a science class, and she's got some clock going, and at 2 seconds, 6, 8, 12, and 14, she measures how far object 1 has traveled, and we'll call that d sub 1, right? And then how far object 2 has traveled. And what we know, or what we're told in the problem, is that one of these two distances is proportional to the time that the object has been moving. Which one is it? So what I'd like you to do is play around with your calculator, and I think a calculator is helpful here, and just do some division, right? Figure out whether or not those ratios between the distance and the time, don't do the ratio between the distance and the distance, just the ratio of distance to time, is that a constant or is it changing? For one of them it'll be a constant, for the other one it'll be changing. Pause the video now and play around with this a bit. All right, well hopefully you found out that it was object number 2, all right? But let's just kind of take a look at how you can figure this out. I'm going to bring up my calculator, all right? I'm going to just kind of set it right here so we can see kind of both the calculator, and let me kind of move it over here. We can do that just fine, all right? So let's first play around with, the first one, right? Object number 1. We have a distance of 9 compared to a time of 2 seconds, a distance of 24 compared to a time of 6 seconds, a distance of 30 compared to a time of 8 seconds, etc. So if that first object had a distance proportional to the time, then if we do 9 divided by 2, 24 divided by 6, 30 divided by 8, 42 divided by 12, and 45.5 divided by 14, then we should always get the same number. And we can test that very quickly on our calculator, right? We can say, all right, let's do 9 divided by 2, and that's 4.5. I don't think we need our calculator for this one, but we'll use it anyway. 24 divided by 6, and that's 4. 30 divided by 8, and that's 3.75, and I'm going to stop right there. All right, I'm not going to even go any further. I wouldn't have even had to go any further than just testing the first two. The plain fact is because 9 divided by 2 is 4.5, whereas 24 divided by 6 is equal to 4, immediately tells me, because those two ratios aren't the same, that the distance that object 1 has traveled is not proportional to the amount of time that it's traveled. But let's take a look at object number 2. Let me kind of clear this out here. Right, in this case, if I look at that 7, what are my units here? 7 feet, right? 7 feet divided by 2 seconds, we find 3.5. Then if I do 21 divided by 6 seconds, we get 3.5. If I do 28 divided by 8 seconds, I get 3.5. If I do 42 divided by 12 seconds, I get 3.5. And finally, if I do 49 divided by 14 seconds, I get 3.5, right? And so what I see in this case is that every time I do this distance divided by this time, right, distance 2 divided by the time, I'm always getting 3.5. All right, so let's kind of just fill in letter A real quick. One of the two objects has a distance that's proportional to time. Determine which one. That is going to be object 2. And it's because d divided by t is equal to 3.5 always. If there was even one of those that wasn't 3.5, so it's not good enough to have two of them. If even one of those didn't turn out to be 3.5, then we would know that the distance wasn't proportional to time. Let's take a look now at letter B. For the object whose distance is proportional to time, what is the constant of proportionality? Include proper units. All right, well, we actually have it. The constant of proportionality is right there, 3.5. But what are the units, right? Well, this gets into the units of ratios, right? The units of a ratio. And the units of a ratio are pretty easy, right? So we could just take even one of these, right? Where we have 7 feet divided by 2 seconds, and that was 3.5 feet per second. Right? And this is a great example of what's known as a unit rate when we talk about ratios, right? A unit rate is always the sort of numerical value you get when you divide out the ratio, right? The ratio is 7 feet to 2 seconds, but when we do 7 divided by 2, or 21 divided by 6, or 28 divided by 8, etc., right? We're always getting 3.5 feet per second. You always want to read the units of a ratio or a rate as the units of the numerator, the fraction bar is the word per, and then the units of the denominator, 3.5 feet per second. Now, what's great about having the units there is it actually makes part C pretty easy. Let's take a look at C. What is the meaning of the constant you found in B? What does it tell you about the object, right? So what does this tell us about the object? Well, it tells us how fast it's moving. It's the speed of the object, right? Right? It's the object's speed, which is how fast it's moving. Right. Now finally, letter D. Write an equation for the object's distance d, given the time t it has traveled for the object from B. Use it to predict how far the object has moved in 20 seconds. All right, so this is pretty easy, right? What we know is that for object 2, we know that the distance divided by the time is always 3.5. Now we can use some algebra by just multiplying both sides of this equation by t, and it cancels, right? So the distance now is simply 3.5 times the amount of time. So this question asks us for two things. One, it asks us for an equation that simply relates the distance to the time by using that constant of proportionality. All right. And it also asks us, how far does it travel in 20 seconds? Well, that's pretty easy, right? Because now we can just substitute 20 into this equation, right? And we can say D is equal to 3.5 times 20, right? And that kind of makes sense, right? It's moving at 3.5 feet per second. So if I take my 3.5 feet per second and I multiply it by how many seconds it's traveled, 20, it tells me that it's gone 70 feet. Okay? And that really gets at a lot of important ideas in terms of two variables that are proportional. One, and most importantly, that when we divide the two, it's always going to give us the same quotient. It's always going to give us the same number. In this case, it was 3.5. We can then use that to write an equation that relates the two variables together, and then we can use that if we need to. All right, so let's move on and let's do some more work with proportional variables. Let's take a look. Exercise number 2. At a gas station, the total cost of gasoline is proportional to the number of gallons purchased. If 8 gallons of gas cost $30.32, then how much will 10 gallons of gas cost? Set up and solve an equation to find the answer. All right, so remember, if I'm telling you that the cost is proportional to the number of gallons, let's kind of circle that. The total cost is proportional to the number of gallons. That means that when I divide the cost by the gallons, I'm going to get a constant. I'm going to always get the same number. When I divide the cost by how many gallons I have or how many gallons I purchased, I'm going to get a constant answer. But that allows me to set up a really nice, easy equation, right? I can say, all right, if I take the cost that I'm looking for and I divide it by the 10 gallons, right, that I'm working with, that should be the same thing as if I took the cost that they gave me, 30.32, and I divide it by 8 gallons. By the way, notice, right, when we set one of these up, I have a cost in the numerator here, and I have a cost in the numerator here. I have the number of gallons in the denominator here, and I have the number of gallons in the denominator there. That's actually why I put these units on there, just to kind of be able to keep track of that. Now, when I actually do the algebra, which I'm going to do by doing cross multiplication, remember that from previous years, I can just kind of cross multiply like this. Then I'll get 8 times C is equal to 10 times 30.32. I can do the next step without a calculator because multiplication by 10 is pretty easy. That would just move the decimal place 1 unit to the right. And now I think I might end up using my calculator to divide both sides by 8. We'll find that the total cost is 303.2 divided by 8. And we find that it'll cost $37.90. You see this a lot when you're working with two variables that are proportional to each other. And what I mean by you see this a lot is you get a pair, right? 8 gallons goes with 30.32. And then you're looking to fill in the missing part of another pair. I don't know what 10 gallons costs, right? So I've got this pair, 8 gallons costs 30.32. And then I've got the 10 gallons, but I don't know how much it costs. So I can always set up this ratio equal to this ratio. This is what's called a proportion. Anytime you have a ratio equal to another ratio in equation form, then you have what's known as a proportion, which kind of makes sense given that we're dealing with proportional variables. Okay, let's keep going. See what we've got next. Let me move my calculator a little bit out of the way. So, ratios of lengths that get scaled in images are really good examples of constant proportions. And you saw scaling a little bit back in Math 7, but it's the easiest idea on earth, right? If you've ever taken a picture with a digital camera, right, and then you've taken the picture and either stretched it to make it bigger or shrunk it down to make it smaller, right, that's scaling, okay? So let's take a look at an example of that in the next two exercises. Exercise number 3. A rectangular image was originally 2 inches by 5 inches as shown. It was scaled up in size so that its smaller dimension was now 6 inches. Letter A, Lengths in image 2 will be how many times greater than lengths in image 1? All right, well, this is actually quite an easy problem. All right, when you just look at this, right, here we've got this image and we've kind of blown it up to make it into this image. All right, so very simple. How many times greater are the lengths in this image than the lengths in that image? Pause the video now and you should be able to write down a very easy answer. Well, it's as simple as this, right? That 2 inches became that 6 inches, so therefore 3 times greater, right? 3 times 2 is equal to 6, so what I did is I just tripled all the lengths, all right? Which makes letter B quite easy. What is the longer dimension of the rectangle in image 2? Well, that's simple, right? If all the lengths get scaled by a factor of 3, then all I have to do is take this, multiply by 3, and I'll find that this is 15 inches. All right, very, very simple. And of course, it's very, very simple in this particular problem because it's just a 3 times. So anytime we have like a nice integer relationship, a nice whole number relationship, oh, the lengths were doubled or tripled or quadrupled, you know, we multiplied by 2, 3, 4, 5, etc. It's pretty easy. But many times those constants of proportionality, which in this case was 3, all right, many times those constants of proportionality are not that nice. So let's take a look at an example of that. Aw, kitty cats. All right, exercise number 4. An image of a cat was originally 1.5 inches wide and 2 inches tall. It was scaled down slightly such that its new width was 1.25 inches. What is its new height, h, to the nearest hundredth of an inch? All right, well, I'd like you to pause the video right now, play around with this, and see if you can figure out the height of the new image to the nearest hundredth of an inch. All right, let's do it. So, what do we know? Well, we can think about it this way. Let's take a look at these two that we know, right? There's been some scaling factor, some constant of proportionality, that when I did 1.5 inches and I multiply it by that k, all right, I'm gonna get my 1.25 inches, right? So when I take my length here, or my width, 1.5 inches, and I multiply it by my scaling constant, I'm going to get my 1.25 inches. So that scaling constant is 1.25 divided by 1.5. Now this is going to be a little bit ugly, so let's bring out the calculator. Right? So let's clear it out. 1.25 divided by 1.5, and we're going to get 0.83 repeated. All right, and that's my scaling constant, right? That's my constant of proportionality. And note, it's smaller than 1 because our image got smaller, right? We went from this bigger image down to this smaller image. But now it's quite easy to figure out the height of this image by simply scaling this constant by the same amount. So I can now say that h is going to be equal to k times that 2 inches. So that's going to be 0.83 repeated times 2 inches. And that is going to be the following. Actually, I should have kind of left that there, but I'll just type in a bunch of 3's. That should be good enough. Times 2 equals 1.666 repeated, and that to the nearest hundredth of an inch will be 1.67 inches. All right. Now, I like kind of thinking about it this way because literally we're going to be getting into some work in the next lesson where we're taking lengths or widths or heights or whatever, like distances between 2 points, and we're going to be scaling them by some scaling factor, just as we did here. You could do this problem kind of like we did the last problem directly with ratios. In other words, you could say something like this. You could say, well, if I take that height and I divide it by this height, right, then that would be equal to this divided by this. All right, and then you could solve this proportion using cross multiplying, right? And you're still going to get 1.67 inches. We'll do it that way in the next problem. Let's take a look at one more problem where we do some scaling. All right, let me get this out of the way. Maybe get this out of the way, still no. All right, here we go. Exercise number 5. On a set of architectural plans, 2 inches on the drawing scaled to 17 feet in real distance. If the plans included a building that was 130 feet tall, how tall was it on the plans in inches? Round to the nearest tenth of an inch. All right, so architectural plans or maps or whatever where we've drawn something, right, that's much smaller than it is in real life, or even something that's much bigger than it is in real life if we were to draw like a bacterium or something that's really, really tiny, right? They always have some kind of a scale. And in this case, what we know is that 2 inches scales to 17 feet, all right? But we want to know now, if we've got a building that's 130 feet tall, how big should it be on the plans? Well, let me let that be h. So I'm going to let h be the plan height, right? How high is it on the plan? Now, what I know, right, is I know that if I take 2 inches and I divide it by 17 feet, that would have to be equal to h inches, because that's what I'm looking for, divided by 130 feet. Right, again, it's just that constant ratio, right? 2 inches to 17 feet equals 8 inches to 100, h inches, not 8, to 130 feet. And now I can solve this by cross multiplying, right? So I'll cross multiply here, 17 times h is, well, 17 times h, and 2 times 130, we're just going to do that in our head, is 260. Now we'll just divide both sides by 17. And for this, the calculator is the better move. So let's do 260 divided by 17, and it should be 15.294, etc. They want it to the nearest tenth of an inch, so 15.3 inches tall. All right? And again, this is very often done on architectural plans when you're trying to scale something, right? And you say, all right, well, I know that I want 2 inches on the plan to be equal to 17 feet in the real world, right? But now I've got, maybe some building that is 130 feet tall in the real world. How tall should I make it on the plans? Well, I should make it 15.3 inches on the plans. All right, let's wrap this up. We are going to be working a lot with proportional variables throughout this unit. This unit's actually really all about them. You're going to constantly see issues where we talk about ratios and scaling and constants and things like that. So today we wanted to just set the basis for that by reviewing a very simple idea. When 2 variables are proportional to one another, then their ratio, i.e. when you divide one of them by the other, that ratio is constant. The constant has a name. It's called the constant of proportionality. Sometimes it even has units that are rate units, something per something else. All right. Sometimes it's just a straightaway kind of multiplier. We multiplied this drawing by a scale factor of 3 to make it into this drawing. And in that case, there aren't particularly units to that scaling factor. We're just multiplying everything by 3. All right. We're going to get a lot more work with these ideas throughout the unit because they're all over the place. For now, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. Until next time, keep thinking and keep solving problems.